Hello and welcome to a little video. This time I'm doing this for my little extension club at lunchtime, and anybody else who's interested, I'm going to try and post these all. I'm trying to do different topics which come up in the extension papers, whether it's STEP, MAP, BMO, AEA, who cares what the exam is called. All we care about really is how we do these interesting questions, and they have lots of interesting questions. And what's more, it's my strong contention that if you can work for a fair bit of time on a lot of these extension questions, obviously your mathematical skills get better, yeah, and so you end up getting better scores in, maths and further maths at A level. I do strongly believe that, and anyway, regardless of grades and scores and everything else, which we all obsess about, we're only human. What sometimes is more important than like the next exam you face is the long game, do you want to actually understand this for your future? It's really useful to actually understand things in life. It always is, and you're always learning. Anyway, and we all make mistakes, and etc., 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 and all the cliches that we tend to use. But it is the reason why it's a cliche is it's all true. Anyway, I'll get on with it. So this one we did at lunchtime today, and I wanted to go through it just because there's definitely one recently in paper 2020, 2021, 2022, I can't remember if it was step 2 or step 3, where they had a modulus question, where if you've done this question first, you would have got it right, yeah, almost all of it correct, probably like 18, 19 out of 20, which is a fantastic score on a step paper in step 2 or step 3, and all you had to do was do this old question from 1997, back when I was 18. If you'd done this first, it would have really helped, because the way I'm going to do this, yeah, this is my idea. I'm basically going to sketch y equals this horrendous modulus expression, and I'm going to sketch y equals x plus 2, and I'm going to see where they intersect. Now, what's really useful about learning this new technique, where I'm going to use a technique which involves using critical values, and I'm going to do that in the next question as well, is you can use this for normal sketching of the modulus function, and you may well prefer it. Yeah. Now, what am I getting at here? I'm talking about critical values. Now, let's talk about critical values. Critical values are where a modulus expression, or expression within the modulus, goes from positive to negative. Now, why would I describe it as critical? Well, because the modulus does nothing to positive numbers. So if what's inside your modulus is positive, then you can just ignore the modulus, yeah? And if, on the other hand, what's inside your modulus is negative, then you have to change the sign on everything inside the modulus. And that way you can abstract away from the modulus. You can get away, sorry, not abstract, but you can get away from the modulus sign and not have to worry about it. So I'm going to do this by basically turning it into a series of expressions that have nothing to do with a modulus. And firstly, I'm going to note the critical values. Now, what are the critical values? The critical values are where any one of these moduli go from positive to negative. Now, here, in other words, they're where it equals 0. Yeah, because when you go from positive to negative, you have to cross over 0. So where is this one 0? At x equals minus 1. Yeah? Where's this one 0? Well, when x is 0. Where's this one 0? Well, when x is 1. Where's this one 0? When x is 2. Yeah? That's from the original question. Minus 1, 0, 1, 2. I'm sure they did that on purpose. Now, what that means is we can be really systematic. We can basically work out what is going to happen when x is less than minus 1, what is going to happen when x is between minus 1 and 0, what's going to happen when x is between 0 and 1, 1 and 2, and then finally if x is bigger than 2. Yeah? And I'm going to have a little table for this. Let's set up a giant table, because this table's really going to help me. Okay, I'm going to talk about, because if I'm just talking about what's happening when x is less than minus 1, I can actually get away from the modulus now, because if x is less than minus 1, let's say minus 2, then you're going to be doing minus 2 add 1, which gives you minus 1, and then you're going to apply the modulus, which makes it positive 1. Now, another way of making something positive when it's negative is timesing it by minus 1. In other words, what you've really got there is y equals minus x minus 1, yeah? I'll do the rest of this in a second. I'll do that in a second. But let me just explain this bit. What I'm saying is basically, let's say if x was minus 10. What you do is minus 10 plus 1 minus 9, and then you make it positive 9. Well, look at this. Now I've written it like this. I'm going to get positive 9 when x is minus 10, because I'd have minus minus 10, which is 10, take away 1, 9. Basically, when x is less than minus 1, this will always take the value of the minus of x plus 1, which is minus x minus 1. I can apply exactly the same technique to the next one and say that's the same as minus x, because this will be negative as well, so I'll need to times it by minus 1, and that becomes plus x. I can take exactly the same approach here and make that plus 3 times 1 minus x. I've times this bit by minus 1 this time, yeah, because I did times that by minus 1 because I made it minus x, but then I've got minus x, which makes it plus x, and this bit's going to become minus 2 times 2 minus x. Now it makes sense to simplify at the end, yeah, so we'll do our working out here and we'll have our simplified form here. And what we're going to create basically is what's called a piecewise function, yeah? And I'll draw it like that afterwards. Now let's simplify this. Minus x plus x, that's 0x, minus 3x plus 2x, that's going to be minus x, and then minus 1, add 3 is positive 2, take away 4 is negative 2. Yeah? I'm now going to do the same here. But on the next bit, if x is between minus 1 and 0, this is now positive, yeah? Let's say x is minus 0.5. After you add 1, you're at 0.5, and the modulus is doing nothing, which means that's just going to remain as x plus 1. But all of the others will still be negative, because if you're at minus a half, that will be negative, that will be negative, that will be negative, and so we need to times them by minus 1. And so we're going to have exactly what we had above, basically, plus 3 times 1 minus x, minus 2 times 2 minus x, and so we get y equals here. What do we get? X plus x is 2x, minus 3x is minus x. And then we've got plus 2x. We're going to get x, I think. And then 1 plus 3 is 4. Take away 4 is 0. So you get y equals x there. Okay, similarly for this one, and you're probably going to get a bit quicker now because you're going to realise this is x plus 1. This is going to be minus x because this is now positive, yeah, because you're between 0 and 1, but the other two are going to be still switched round, and then we're going to simplify it, and so we're going to get x minus x at 0 minus 3x plus 2x is going to be minus x, and then 1 plus 3 is 4, minus 4 is 0, so we're at y equals minus x there, and then from 1 to 2 we're going to have x plus 1 minus x plus 3 times, this is positive this time, x minus 1, but this is still negative. Simplify it, and we get y equals, right, there you go, that becomes 3x plus 2x, you get 5x, I think, there, and then 1 plus 1 minus 3 is minus 2, minus 4 is minus 6. And the last one, this is where, if x is bigger than 2, you can ignore the modulus sign here, can't you, because nothing's going to be negative. So it's just going to be x plus 1 minus x plus 3 times x minus 1, minus 2 I wrote there, that's a bit of a mistake. Minus 2 times x minus 2, and we can see what this gives us. What does this give us? X minus x is 0, 3x minus 2x is x, and then 1 minus 3 is minus 2, but then we get plus 4, which is x plus 2. Cool. Okay, what that means is this can really, and any equation which you write like this with a load of moduluses can be written like this, yeah? And you'll see if you're doing 2020, 2021, 2022 step papers, there's a question just like this somewhere, can't remember what it is. What we can say basically is our equation is f of x equals minus x minus 2, whilst x is less than minus 1. Have you seen equations written like this before? I bet you have. X when x is between 0 and minus 1 and 0. Writing that wrong, sorry. And then minus x when x is between 0 and 1. And then 5x minus 6 when it's between 1 and 2. Missed a little less than. And then finally x plus 2 when x is greater than 2. That's our whole curve. And with these piecewise functions, you can just draw them bit by bit. Yeah. Now, I've been a bit lazy here. I'm going to be using GeoGebra basically to draw this, and I'll show you. I'm going to type in fact, as I'm doing a screen share, let's just quickly show you by doing it on here. If I type in the command, by the way, for on GeoGebra or Desmos for this, abs, it means absolute value. It's the modulus. Now, what was it we had? We had, I've even forgotten, x plus 1, I think, first. I think it was minus a mod x, so minus abs x. And then it was plus 3 times abs of x minus 1, and then minus 2 times abs of x minus 2. Okay, enter. Sure enough, let's check our answer. Let's take a screenshot of that. So there we go. And by the way, these old step questions, especially when they're about graph sketching, this is the way to check them, isn't it? You get some graph drawing software, because it's got really good now, the graph drawing software. And so it draws mod graphs like that, no problem at all. So let's just have a look at it on this page. Sure enough, that line there is y equals minus x minus 2. This line here is y equals x. Then from 0 to 1, it's minus x. Then from 1 up to 2, it's 5x minus 6. And then from 2 onwards, it's x plus 2, because look at that, it's going through x plus 2. So, with that in mind, we can now answer the question. Yeah, we've done all the hard work. We can now find where this equals x plus 2. Yeah, and we can do that just by drawing the line x plus 2 crudely over the top. Now, why is the line y equals x plus 2? Well, the line y equals x plus 2, when x is 0, y is 2, and y is 0, x is minus 2, it's going to look something like that. Oh, sorry, I'm not exactly steady Eddie with my hand. Okay, so where do these graphs intersect? Well, they intersect when x equals minus 2 or when x is greater than or equal to 2. So it's got an interesting solution set. It's got one little value over here, but if you pick any x value greater than or equal to 2, the equation will be satisfied. Yeah? And that's that one done. So that's how you handle the modulus, critical values. Incidentally, if you've got to sketch an awkward modulus graph, that, I don't know, 3 minus 5 mod x plus 3, you can sketch that using critical values. Your critical values here will be when x is less than minus 3 and when x is greater than minus 3. And when you come up with your two lines, and you come up with something, I don't know, it's going to be something like when x is 0, what is that? I'd have to work it out, but when you come up with your upside down mod graph, one side of that line is going to be when x is, it will be on the other side because minus 3 is a critical value, isn't it? When one of your lines is going to be when you consider x is less than minus 3, and then other line is going to be when x is greater than minus 3, and that's just normal x plus 3. But when it's less than minus 3, that's going to turn into minus x minus 3 in brackets, and you'll need to apply it. It's really quick to do. You could easily do it. So bear that in mind. That gives you another way of handling these modulus questions at A level. Okay, let's try another one. Yeah. Oh, look at this. We've got more graph sketching. Sketch the following subsets of the xy plane. Yeah. Now I'm going to use really similar approaches with critical values. Now here, look, not only x is in a modulus, y is in a modulus. So okay, let's kind of think about it tactically, because we're going to have to think about when x is less than 0 and, let's write it down, x is less than 0 and y is less than 0. Yeah, we're going to have to do all possibilities. When x is less than 0 and y is less than 0, then, and by the way, I'm going to ignore the inequality, because I can handle the inequality as a region. When it says subset in the xy plane, it means region. So I'm just going to think of this as an equals sign first, and I'm going to draw the straight lines. Now, when x is less than 0 and y is less than 0, you're really going to have minus x here plus minus y, yeah? And this is going to be equal to 1. So ignore the inequality for the moment. Now, what is this? This is minus, well, if you like, this is y equals, after I've added that over there and it's taken this over here, minus x minus 1. So what that means is basically when x is less than 0 and y is less than 0, yeah, you're going to actually be using the line y equals minus x minus 1, which goes down and passes through minus 1 and minus 1, yeah? Now you might think, why haven't I drawn it continuing on from there? Well, that's just because straight away I'm using my problem solving skills and I'm realizing this equation can't be true if x was bigger than 1 or less than minus 1, or if y was bigger than 1 or y was less than minus 1, because you're immediately taking a positive value, the magnitude of it, and there's no way that can be equal to 1 when you're adding another positive value. So I know it's only going to go from minus 1 to 1. Yeah. Now, it doesn't take too long to think, well, okay, what about if x is greater than 0 and y is greater than 0? In other words, they're both positive. Well, then you've just got x plus y equals 1. And so y is 1, take away x, yeah? And so we're going to have a negative gradient, but it's going to go through 1 and 1, yeah? Now, what about if x is less than 0 and y is greater than 0? Well, in that case, x needs to become minus, but the y can stay positive, and you've got y equals x plus 1. And so you're going to get this. You're going to get a lovely little diamond, aren't you? And then when x is greater than 0 and y is less than 0, guess what? You've got x minus y equals 1. And so y equals x minus 1. and that looks like that. And therefore, if we've got to sketch this where it's less than or equal to 1, we'll pick a point, yeah? Most people pick the origin, so do I. 0 plus 0 is less than or equal to 1, so this lies in the region, and therefore it's all points in that diamond, yeah? Now, I have actually already prepared this. I drew this on GeoGebra a second ago, just to make things easier. You know, abs of x plus abs of y equals 1. I don't know why it didn't show it as a modulus. I guess because it's implicit. I don't know. But yeah, that's what it looks like. Sometimes GeoGebra has a little bit of trouble. Maybe it's just a graphics card in my computer, but yeah, that's what it's going to look like, and it's going to be the region within. Maybe I should have made that a less than or equal to. Should I do that? Just by less than. Oh, did it not like that? It didn't like that, did it? Where did it go? I don't even know where it went. Edit, undo. There we go. Can I not change that into less than or equal to? Less than or equal to. And then press enter. It just disappears. Okay, it really doesn't like me doing that. Sometimes the graph drawing stuff doesn't quite work out, but yeah, sometimes it does. Okay, so we've figured it out anyway. We don't need GeoGebra. Just take the equality case. The region should be obvious. Okay, what about this one? Well. I think it's safe to say that when a function gets, I mean, we could do this with critical values. You could say, you know, we're going to do exactly the same as before, essentially, but rather than using zeros, we'll be using ones. We'll be saying when x is greater than 1 and y is greater than 1, well, then they're both positive, and so you've got x minus 1 plus y minus 1 equals 1, and then you'd have x plus y, therefore, add the two ones over onto this side, x plus y equals 3, yeah? And, you know, by a similar argument, basically, you're just going to have this coming down from, and it's not going to go down from 3 to 3 actually, because can you see that you can't have x is 3 and y is 3 here, because you're going to have 2 plus 2 and that equals 4, so it's not going to quite go that far. But through similar reasoning, all of this is pointless anyway. I'm saying you could do the whole thing again, but isn't it better to just notice that if f of x ever becomes f of x minus 1, that just moves it 1 to the right? Yeah, and what's more, if you ever replace y with y minus 1, that moves it 1 up. Now, you might not be aware of this one, because when you're doing function transformations, we always treat it as y equals f of x becomes y equals f of x plus 1 to move it up. But what's really happened is we've actually swapped it with y minus 1. In other words, we've replaced y with y minus 1. Yeah, and you can see that on circles, can't you? Because if you've got x minus 2 squared plus y minus 3 squared equals, I don't know, 25, well, that's a circle, centre 2 across, 3 up, yeah, and then radius 5, yeah? And so, you know, we're just moving it 2 across, 3 up. So all we've got to do for this next one is just move the last one, 1 to the right and 1 up, that diamond shape, 1 to the right and 1 up. And so, and we'll check at the end on GeoGebra if it works. If I'm moving that minus 1, 1 to the right, I'll be at 0, 1 up, I'll be at 1. It's a diamond, basically, with that bit starting at 1, so it's going to be like this. It's going to be at 1 and 1. And then you're going to have this one up here, this one up here, and this one up here. This is part of the line y equals x plus y equals 3, by the way, if you're wondering where we got that from. And that is going to be the region which has all the points which satisfy that inequality. I hope it makes sense, my strategy on that one. It's really just a function transformation. Okay, 3. Ooh, look, they changed that plus to a minus. That's going to make a big difference. You've got to be careful of that. You know, you might think, it's just a minus, but it could change everything. So we're going to be systematic again. Right, mod of x minus 1 minus mod of y plus 1 is less than or equal to 1. Let's write that down. Mod of x minus 1 minus mod of y plus 1 is less than or equal to 1. So yeah, how could we handle this? I don't like the minus there. I really don't. I'm actually going to add this to the other side so that I've got mod of y plus 1, add 1, equals mod of x minus 1. I just feel more comfortable looking at that kind of idea, yeah? But then I am going to take very similar ideas to what I did before. I'm going to think about the critical values, yeah? Now the critical values are x equals 1 and y equals minus 1. Yeah, they're clearly the important values. Yeah, so let's think about it systematically as we did before. Yeah, okay, if x is greater than 1 and y is bigger than minus 1, that's probably the simplest situation to consider, because then these are all positive, aren't they? Yeah, and so we can ignore the modulus signs and we get y plus 1 equals x minus 1. And so that's going to give us, if we rearrange this into our typical straight line equation, y equals x minus 3. Yeah, and so provided we're at that point when x is 1 and y is minus 1, well, x is bigger than 1 and y is bigger than minus 1. Now let's find that on our graph. X is 1, y is minus 1. Yeah, that's that point here. Yeah, okay, right, good, we've got that. And what is that going to give us? That's going to give us this equation, which is, let's just get it right. Yeah, I'm just checking my reasoning here. When x equals 1, we're going to have 0 equals, and this would have to be, is it possible for x equal to 1 and y equal to minus 1? I have to be slightly careful here. I'm going to draw this anyway. Y equals x minus 3, and so that would obviously be passing through minus 3. I'm slightly nervous about this, but I'm going to draw it there anyway. Yeah, cool. Yeah, happy with that. Yeah, I'm going to point out that passes through at 3. I'll tell you why I'm slightly nervous as I'm doing this question. I'm just thinking about the case when we have these critical values here. If x was 1, we'd have 0 on the right hand side, and if y was minus 1, we'd have minus 1 plus 1, which is 0, plus 1. Yeah, that looks to me to be an absolute contradiction. Yeah, it means that point can't be on this line. It's why I'm nervous, and the reason is basically I don't think this curve is defined between x is 0 and x is 2. Can I just quickly justify this as well, because this is a crucial part of the argument and it's where the question is quite subtle. Yeah, what we're going to do, if we look at this, are there certain values which x isn't allowed to be? Well, can you see on this side that this side is always going to be greater than or equal to 1. Yeah? There's no doubt about that, because you've got a positive number plus 1. So that's always going to be greater than or equal to 1. Well, is it possible for the right hand side to not be 1 or bigger? Yeah, it is. Yeah? If x was, for example, up to, well, if x was 0, that's fine. Yeah? But if x was between 0 and 2, yeah, then it's not possible for this to be, then the right hand side is going to be less than 1 and the left hand side is going to be greater than or equal to 1. So I think actually my straight line is slightly wrong. It's the right straight line, but it's not going to be defined, the curve, and this is an important thing to recognize, from 0 to 2. It's not going to have any values, because if you have a value of x between 0 and 2 here, you end up with a contradiction. There's no y coordinate, which after you add one and take the modulus and then add another one, equals the right hand side here, because the right hand side is going to be less than 1. And I hope you can see that. For example, when x is 1, the right hand side is 0, and that's impossible. So x isn't defined between 0 and 2. If you like, the domain is x, x is greater than 2 or x is less than 0. And I think it can be, x is greater than or equal to 2 or x is less than or equal to 0. So watch out for that. Yeah. Now, because that almost caught me out there. Now, what about if x is greater than 1 and y is less than minus 1? It gets a bit easier now, because if x is greater than 1, y is less than minus 1, we just make that minus y minus 1 plus 1 equals x minus 1. The right hand side doesn't change, because x is, the right hand side is positive and the modulus is doing nothing, but on the left hand side the modulus of y plus 1 is negative, because y is less than minus 1. And so now we can just rearrange it, they cancel, and we're going to end up with y equals 1 minus x. So I think from here, below minus 1, this is supposed to be at minus 1. It will be easier when I show you the GeoGebra version in a second. you're going to have y equals 1 minus x, which looks something like that. Yeah? We'll talk about the inequality at the end. Now, what about if x was less? Now, here's the thing, we're not going to be using here x is less than 1. Yeah, I should have been using x is less than 2 because x can't be between 0 and 2. I should really be considering x is greater than 2 each time. And now I'm going to be looking at x is less than 0 each time. So x is less than 0, y is bigger than minus 1. We're going to have y plus 1 equals, now the right hand side is going to be negative, so this is going to be 1 minus x, and so this is going to be y equals, I believe, minus 1 minus x, yeah? And what does minus 1 minus x look like? Well, we've got x is less than 0, y is bigger than minus 1 minus x looks like this. I think we had it come up earlier. It's just a straight line like that. And the last little bit, it's going to be easy. X is less than 0, y is less than minus 1. So we're going to have minus y minus 1 plus 1 equals 1 minus x. And we get, they cancel, so y equals x minus 1. And it looks like that. So your final sketch, if you do it nicely, should look like this. But yeah, it's subtle, that bit, when you've got to realise that x actually can't be between 0 and 2. When somebody shows it to you, it's obvious. Now, these are the straight lines. Now, if we want this to be, we can just do the pick a point argument here, just like we always did regions at GCSE. If you're doing less than or equal to 1, you want a point basically which satisfies that. So let's just take a point which is in the middle bit, if you like. Let's just take 0, 0, in fact. Does 0, 0 satisfy this equation? So let's have a look. We get 1, take away, like x is 0, y is 0 is the point I'm picking. 1, is that less than or equal to 1? Yes, it is. In other words, the region they want is in the middle here. And so that is going to be the region that we want, yeah? And you can, if you want, you can check and think, well, what about minus 3, 0 over here? Yeah, does that not work then? Let's have a look. We get minus 3 here, minus 1, well, that's minus 4, mod it 4, 4 take away, 1, 3, no, that's definitely not less than or equal to 1, so you can see we've shaded the right region. Okay, sorry about my terrible sketching there. It's hard on a graphics tablet. Right, last one to do. Mod x, mod y minus 2 is less than or equal to 1. This sounds more interesting. Mod x, mod y minus 2 is less than or equal to 1. Well, let's consider the equality case so we can sketch it. And we can safely divide that, well, because we're considering the equality case, and also because that's strictly positive. So we need to be sketching mod of x is equal to mod 1 over mod of y minus 2. I'd normally like y to be the subject, so I'm going to have it just slightly the other way around. It's 1 over mod of x, but it doesn't really matter. It really doesn't. Okay, critical values here. Well, once again, let's kind of think, is there something which, x and y can't be? Do we need to worry about certain values here? Well, I don't like division by 0, so I'm going to say let's not have y equal to 2, yeah? And equally, if I've got it rearranged this way round, I'll get division by 0. So x doesn't equal 0. Now remember, when you're dividing by 0, it tends to give you vertical or horizontal asymptotes on your graph, yeah? Because the curve cannot be there. And so it's going to have an asymptote of y equals 2, and an asymptote at x equals 0, which is the y-axis. So it's going to be an asymptote down there. Now, when x is bigger than, clearly the critical values is x equals 0 and y equals 2. Yeah, those are the critical values. So when x is bigger than 2 and y is bigger than, when x is bigger than 0 and y is bigger than 2, what are we dealing with here? Well, this is a lovely case where we can just say it's just y minus 2 equals 1 over x. In other words, it's y equals 1 over x add 2, so it's just like the 1 over x curve moved up 2. In other words, it looks like that, yeah, just like we've always known the y equals 1 over x curve to look like, and I'm not really drawing it very much to scale. I'll show you on a nice GeoGebra picture in a second. If x is greater than 0 and y is less than 2, well, we're just going to have 2 minus y equals 1 over x, and that's the same as y minus 2 equals minus 1 over x. So y equals minus 1 over x, add 2. Now what does that look like? Well, minus 1 over x is actually the one which is in the opposite quadrants to there and there. It actually is here and here, but it's moved up 2. In other words, it's going to come up like that, approaching both the asymptotes, yeah? And it's exactly the same on this side. In fact, it's obviously the same on this side because this is what's known as an even function. And that just means whether I plug in x or minus x, I get exactly the same values out. So it should have reflective symmetry in the y-axis. But you absolutely can do now x is less than 0, y is greater than 2, and x is less than 0, y is less than 2. And you will work out that you'll get exactly the same curves on this side and this side, yeah? Now at the very end, what are we actually finding here? We're finding the region where the product of these two values is less than or equal to 1. Well, let's just take the origin once again. If you had 0 times by 0 minus 2, well, you've got 0 times by positive 2, which is 0. Is that less than or equal to 1? Yes. So we want this region, yeah? The region right in it. Let me show you a picture of it on GeoGebra, what it looks like. Here's one I drew earlier on GeoGebra. That's what it should look like, and we want the region in the middle, and if you pick x is 0, y is 2, you're going to see that works perfectly for that. Whereas if you picked a point like O, and if you pick a point on a line, you'll see the equality case holds. So 1, 1 should be where it equals 1, and sure enough, I believe if I plug in x is 1 and y is 1, I get it equal to 1 here because I've got 1 times by minus 1 made positive, which is 1 times 1, which equals 1. And so there we go. That was a lovely bit of graph sketching, but my main point here is critical values. Particularly if you're doing one of the more recent step papers, you can do this trick for any piecewise function. I think they get you to do it back to front. I think they give you these, and you have to come up with this equation. And because I'd done questions like this before, it made it a lot easier, yeah? That's the thing about maths. There's lots of tricks to learn, and that's why you can prepare for the step, yeah? It's not easy. It's just like, trying to prepare for BMO or something like that. It's not easy. They try and write the questions so you can't have done tons and tons and tons of papers, and it's just about past papers. They do try and do that. But the more maths you've done, the better you get, the more tricks you know, and that's the thing. All good maths questions teach you a new trick, I think, and that's why step questions are really good to do. That's why MAT questions are really good to do. That's why BMO questions are really good to do. Who cares what past paper you got it from? Even the Primary Maths Challenge has some really good tricks sometimes. I'm not joking. Okay, thanks for listening and keep up the hard work. Bye-bye.